Welcome back. Today we're going to be looking at the list data structure as we continue our course on how to build data structures in C++. As you can see, looking in our data members section, we have an additional data member that we had from array. When we're dealing with a list, we often have to access both the front and the end of the list. We added an extra data member specifically so we can get access to that end node. And so we have an end node data point that we're going to use as a reference for that. We also have inside our header section, we have a list of our constructor, copy constructor, and our destructor. We're going to take a look at a couple of those today. And then we have the methods that go along with lists. Now, lists in Java, as well as the actual template, the standard list type inside C++, have lots and lots of methods available to them. We're just implementing a few of these to get started with this today, and so we're going to be looking at the basics to do this. We're going to look specifically at the addAtIndex, addFront, addEnd, and remove methods, so we can see about how those are set up. And then we're going to look at a quick comparison of how the setAtIndex is different from that of the array. Notice specifically the idea that the setAtIndex returns a type, unlike the setAtIndex inside the array class returns a void. Because this one, we're going to continue on with the Java style of approach of whenever you replace a value inside a list, the original value is returned back to you. So we have that information available to us. And then we have, again, our contains method to begin our search structure. So we can use just a basic linear search, going through that and seeing if it has something that's workable with that. And then our standard accessors of getSize, getFront, and getEnd that are of type, whatever type of return, as well as a constant because they are going to be used within the copy constructor. So we're going to go ahead and take a look at that. Let's go ahead and switch to the code for that specifically. We look over here at the header for the class. As you can see, our class header definition looks a lot like our UML. It's one of the nice things about using the UML to help design our class in the first place is it makes it really easy to design the class. Again, in our private data section, we have our data members that belong to this. In our list class, we don't have any private methods we have to worry about for this at this point, so they're going to be only just the data members here. As we get more complex data structures, we're going to see some private methods that will belong to the class as well. But for now, we've just got that. As you can see, we have our organization by constructor, by our accessor methods, and by the more advanced methods. So let's go ahead and let's take a look at the constructor first, using that to actually see how we build the list, and we're going to go and look at the methods we have to use to actually go through stuff. So scrolling down, we have our constructor. As you can see, is our constructor right here. The constructor itself is a lot simpler, much less complex than that of the array. Because when we build an array, we have to define the entire size and structure immediately, holding everything that can possibly hold, knowing the front and getting all the node spots all the way down. However, when we build a list, it's of zero size. There's nothing in there to start off with. And so all we have to do when we initialize our constructor for our list object is initialize all the data members to be basically null or zero. And so we set our size to 0 because nothing's in the list first. Then we set our front and end both to null pointer, and our list is done. We've made our list. Nothing's in there yet. So we can test look and see how that works in just a moment. The destructor for the list looks a lot like the destructor we have inside our array. As you can see, it's condensed down here without any having comments or any count statements that we can, or without having any comments or count variables we can keep track of. It simply just creates a pointer referencing the front and deletes the current front as it moves down the list, deleting all the memory that's allocated this appropriately. So the list destructor, is really easy to take care of. As you can see, it's pretty simple on a linear data structure, not a lot of work that has to go in with that. Let's go ahead and collapse that out of the way. Our getSize, getFront, and getEnd methods are all just regular const methods that are accessors. They look just like every other method we've had where it simply returns the data member that's attached to it. And so that's just really simple, ready to go. They'll look the same for that for the getSize and getFront as well. We're returning the appropriate data member. We want to take a look at the addFront, addEnd, and addIndex methods next. So when we are dealing with a list, there are a couple of different pieces of logic we have to handle when we're talking about either adding to the front or adding to the end. And so I have made separate methods for both of those because they're a little bit different for that. And by making separate methods, it allows us to refactor some of the information of our addAtIndex so we don't have to rewrite the same set of code when we're doing specialized methods of that call. So let's take a look first at the addFront. So if we have the addFront method, we have a little test at the beginning. We have to make sure to see if the size itself is 0, because if size is 0, we have to modify both the front and the end pointer, because there's nothing there, the first one we add will be both the front and the end. And so we have at this point, we create a new node. It's a new node of type pointer first, and I assign it using the constructor, specifically using the idea of value right there. Otherwise, I'm going to use the idea if it's not the first spot, I'm going to make a new node of type pointer, and I'm not assigning the data so we can show you how we can use the different constructors. Again, I set the node data, passing it value. I set the pointer, passing it front, so I'm going to put it, it's going to point to front. I could also go ahead and create the entire node in one single statement right here, where I say node of type pointer new first is a new node of type, and I pass it value and front all at once, so make the connections in one single line. Either way it works, it makes no difference to me. Whatever works best for you and your logic will be fine for that. And then I have to make sure I set front to be the new first, because I have to move the front pointer so it points now to where the new front of the list is. That's what we do on this one right here, but we have to make sure we also do it in that. And again, because we're growing our list, since we're growing our list, we have to make sure that we have a reference to actually show the list is growing. And so our size data member that belongs to the class has a plus plus operator added to it, so we can make sure we're growing the list up by 1 each time we call the addFront method. When we look at the addIn method, again, we create a new node of type data, so I'm using that same structure. Then the idea of size is equal to 0, I'll set this in front to be that new added node. So it's a little bit different version of what we just did up here in the addFront, but I'm doing it all in one single statement right here because I create the single node once right here. Otherwise, if it's not the size 0, then I set end, I'm going to point into this new node that I just had because I have a reference right here too. I know where added is, so I can tell end to point to that. And then because end is no longer the end, I have to adjust end, and so end is now pointing to added. So I'm assigning the value of added now to be where we're pointing to that. And size will go up by 1. Okay, same basic approach. So let's go ahead and let's take a look at the addIndex method. That's the next one we have on here. Now, with the addIndex method, we're going back to our standard approach of using the assert. We have to make sure that our index we're passing as a parameter is a valid location. We can't just simply throw things about willy-nilly. So we have to make sure the index is greater than or equal to 0 and index is less than or equal to size. What? Less than or equal to size? Why, yes, it's actually okay. Because if you're actually adding at size, so if you have a list of size 3, that last spot is 2, so size 3 would be adding it to the end. It's totally okay. And so what we do is we use the ability to refactor our code. And so we have if index is equal to 0, then we're just going to call addFront and pass it value. And then if index is equal to size, we'll just call addIn and pass it value. Now, we don't have to worry about doing size plus plus because size plus plus in every other case is handled right here inside the else. And you can never get inside that else if you do it if it passes either of those two first cases. So we're good to go for that. Now, if we have, however, an index that's somewhere different from this, we have to actually go through and figure out where to go. So we're going to use our pointer chaining to actually go through that. And so I created a node of type pointer called inserted node, which is the brand new node, the one we're going to put inside here. And I create it with a type value. I do not know which node I'm going to be putting it next to, so I don't want to specify the idea that's going to go for that yet. I set a current pointer to be front, and a previous pointer to be no pointer. Because when I'm moving things around, I have to keep track of it on there. And we'll have a lecture on the board to go along with this as well, so you can see this in a visual fashion. But the idea is that we always have to keep track of where we were, as well as where we currently are, because when we make an addition, I have to be able to point this one to me, and then point that one from me to there. Otherwise it won't make sense. And so I just use my pointer chain to go through and readjust the value that's going into both previous and current, always moving it to the appropriate thing, going down the chain of pointers. And then once I get to the correct spot, I set previous's node pointer to my new inserted node, that value we just created right here, and then tell inserted node to point to current. So whatever one was right here, I break the little chains and we're connecting them together, make it so it connects to this one, and this one now connects to me. And we're good to go. Size goes up by 1. So addIndex works a lot like the idea of that. It's just doing the actual logic to put that in. So this is the idea of when you're using the add with a 2-parameter method in Java, where you pass up first the index and second the parameter you're going to be assigning to the value. This is the logic that goes behind that. So again, when we're doing data structures, what we're doing right here is we're seeing how we actually build the things we use in our other languages. And so let's go ahead and take this a little bit further. Now, the setAtIndex, and when we did this inside the array class, it was of type void. Because an array traditionally doesn't return anything back when you put something in the value. There's nothing that comes back from it. We're not retrieving values from that. And because we're not doing that, we want to make sure that we actually have our setIndex keep with the Java idea, but when we set something, it returns the associated value. So we make it as of type, and it has the same header right there of index type data. We have the same idea of an assert, again, greater than or equal to 0 and less than size, because we can't retrieve something from the size itself. That's too big. So unlike the addIndex, we can only do a setIndex. We will have to do less than size. We then created a variable of type, remove data, something we can actually hold, so we can assign whatever was inside that spot originally, and we're going to assign that to it. We make our pointer to traverse the pointer chain, going down through the structure. Using that same for loop approach, we're going through, starting at 0, spot is less than index, spot goes up by 1 each time, going up until we get to right before it. Every time we go before it, we move to the next one, so current will point at the end to the one we want. Once we get to that point, we're going to say remove data is going to be current.getNodeData, and I'm going to put that value into that remove spot, replace current's data with this current setNodeData line, and finally return what we took out of that list. So we took that data out and replaced it with a new value with the setIndex method. So it works just like that we saw inside array. So we're really actually pretty similar. The only thing that we have to add is this lovely little line right here where I take care of this and where I return it. Other than that, though, we don't have to really worry about much in the difference between that and an array. The getFromIndex method is just the same. It's literally the exact same thing, except instead of array of type, we have a list of type. So we don't really need to go into a lot of detail on that. Now in our remove method, we do have to, again, assert that we're within the range of this. We can't remove things that aren't possibly in there. And so we're only using the single parameter int-based remove. And so if the index is within the range of size and 0, we can take it out. Again, taking a variable we can use to hold that when we're ready for it. Now, when I'm removing something, I need to actually keep track of 3 different pointers. The current one, the previous one, and the one that I'm going to be taking out that was in between them, so I can actually keep track of that. And so I'm assigning both of the previous and to be removed to be null, and front to be the current. And so I'm going to use that regular idea of pointer chain so I can keep track of this. Now I do want to check to say if index is 0, I have to make sure that I'm going to handle that 0th case then I handle the 0th case effectively. And so if that is going to be the case, I'm going to assign to be removed to be front, and then this dot front is going to be equal to front get node pointer. So I have that right there, so I can actually move the front on that, so I have information as to what I'm doing, because I have to move that over to that next spot. Otherwise, if index is size -1, aka I'm at the end of list, I have another special case. And so if that's the case, I'm going to take my lovely traversal loop, I'm going to iterate over until I get to the spot by doing pointer chaining, just like we've done all the time so far. Then I'll set to be removed to be current. I'll set previous as node pointer to point to null pointer, because the one that I was at before, because it was at the end, I'm going to set that to be pointing to null. I'm going to set end to go to point to previous as well. And again, notice on all of these, I haven't touched anything about that to be removed. All I do is assign that pointer to it, and it still has its value, it's pointing to wherever it is, but I'm not doing anything yet. Now again, I have my final case where it's somewhere in the middle of my list. Again, pointer chaining all the way down, just like normal. Again, I set to be removed to be current, just like I did on the other case. I set current now, because it's the one that's in the middle, I take that to be to be removed's node pointer. So whatever current was pointing to, I move it to the next one. And then I'm going to take the previous one, the one that was pointing to current, I'm going to point it to this new one. So that way I take what was in the middle out, and I take it out and I move it so it's right here. Once I've done that, I'm out of the case of all of these, so I've already gotten rid of all the stuff. I have to be removed holding the value of the node that I'm removing. That's taken out of place all the way through, so whichever one I'm looking at, we're good to go. So regardless of those cases, remove then has the actual one we're going to do. And so I'm going to say the removed data member right here, type removed. The to be removed node, I'm going to get the data from that and store inside removed. Once I do that, I'm then going to deallocate the memory attached to this pointer by calling the delete operator. And so delete to be removed will then remove that value from the memory location, so it's no longer going to be allocated for that. And then finally, I'm going to do size minus minus. That way my size adjustment is handled outside of the actual testing and stuff, so I don't have to worry about doing it more than once. Never want to do that. And then finally, once I've adjusted the size again, as well as removed the actual data from memory, then I return the value that I retrieved from that node. And my remove method is finished. We'll see how that works in just a bit. And then finally, on the contains, when we look at the idea of just doing a quick linear search, all we have to do is start at the beginning and work all the way through to the end and see if it matches. Not a lot of work. And so I have my greatly named method of, I have my fantastically named parameter of find me. And so bool is set to be isInList is set to false. My node type pointer of current set to front. I use my regular chaining on that. And so if current pointer get node data equals find me, then isInList is true and return that variable. Otherwise, I go to the very end and I simply return isInList. Now I could, of course, have that simply just have this one line done once, but I don't want to actually continue going through that list. If I've already found it once, it's good. I don't have to find it a second time. And we can talk about how we can actually do that for doing a more advanced idea, like say, for example, looking at the index of method, or using other features for that in the next version. But as you can see, we have the beginnings of our list structure. We'll talk about more advanced ways to do with lists, including more methods that we can do on the list itself later. Thank you, and have a great day.